This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hey everyone. So today is the first lecture of the FEA lectures. So there are a couple of things that I need to point out before just going through the first lecture. This is my email address. If you need to reach me, just use this email address. I think I'm a little bit faster than Peter to replying back, because I'm not as busy as Peter, but just in case that takes more than a couple of days and you didn't hear back from me, just please send me a follow-up. Yeah. So according to the timetable, we have, I guess, 6 FEA lectures, 1 revision, and the last lecture, which is basically the mid-semester test, which will be held on the 16th of August, I guess, Friday, 2 weeks from now. So during the 6 FEA lectures, we're going to learn about an introduction about the finite element analysis. Like it's very brief because it's not the whole semester, but you're going to learn the fundamental concepts and the basics. So the first lecture is mostly about the introduction, about the numerical solution, especially FEA. And from the next lecture, which is tomorrow, we're going deeper into the math. So in the last 2 lecture spots, like I guess Tuesday and Thursday of the last week, I try to solve more examples and practice more to get you prepared for the mid-semester test. So regarding the mid-semester test, it's not a big test. So you'll be sitting here exactly this theater, and you'll be given like 45 minutes to answer 3 simple questions. 2 of them would be conceptual questions, and the last one is just doing some calculation. And if you just follow up all the FEA lectures and practice the examples that I solve in the lectures, and also just spend some time at home to practice more on the homework and do more, surely you can just get high scores, just like the previous year. And from the next week, the FEA workshops, which we gonna teach commercial finite element software called Abacus, they're really useful. So if I want to be honest with you, the FEA theory, like during the lectures, and just learning how to use Abacus are 2 important skills that could help you in the future if you're interested in working in mechanical engineering, especially in the industries. So yeah, just please stop me whenever you feel something unclear, or if you have any questions. And yeah, so any question about the timetable, about the mid-semester, anything? Otherwise, we can just start the first lecture. So this is a list of some useful books for the FEA. I mostly use the first resource for the FEA lectures here. Like it's called A First Course in the Finite Element Method. It's very straightforward book. It's kind of self-learning, and it has a lot of simple and useful examples. And I mean, after the lectures or during the lecture, if you feel that you want to go to know more about the FEA and go deeper into the finite element analysis, I would recommend you this one, An Introduction to the Finite Element Method, written by Reddy. It's one level more advanced than the Logan books. So what we're going to learn today is we want to know that what's the difference between the analytical and numerical solutions, and also why do we need to use the numerical methods, what's the advantage of them, and then we mainly focus on the finite element analysis, or FEA, and just summarize the advantages of the FEA, and learning the basic concepts which are used in the finite element analysis. So these are the three important questions that we're going to know their answer by end of this lecture. So what is the finite element analysis in a simple language? And why a lot of commercial software such as Abacus or ANSYS or COMSOL use finite element analysis. So Abacus, ANSYS, and COMSOL are three major finite element analysis software which are primarily used in the industrial companies. And the good thing about this software is if you know how to use one of them, you can easily pick up the other ones. It's like an algorithm. If you know algorithm, you can learn the syntax in the different languages, like Python and MATLAB. And this is exactly like that. So you only need to know the steps, how to model, and how to use the finite element analysis. And then, why do we need to learn it? So the short answer is because you need to pass this subject. But the long answer you'll be figure out by end of this lecture. So when it comes to solve an equation, doesn't matter what, like, is it partial, differential equation, or it's a simple equation. There are two main methods to solve the equation. The first one is analytical methods, and the second one is numerical methods. You might have heard about some of the numerical methods like the Newton, Raphson, or Runge-Kutta. So what is the analytical solution? So imagine that we have a function which is called f. F is a function of the x. So we want to know that for what values of x, f of x equals to 0 for this domain of the problem. So if we find an x equals to x1, which is an exact solution of this equation, which means that it gives us 100% accuracy, we call it analytical solution. So analytical solution satisfies the equation all over the domain, and it's fixed, right? There is no error there. So if I want to give you an example, so imagine that function of the x equals to x minus 5. So we want to know that what's the solution when we want to make f of x equals to 0. X would be 5, right? It's very simple. This is the exact solution. There is no error there, and it's true all over the domain. Another example is when you want to solve a quadratic equation, ax squared plus bx plus c equals to 0. You know, there are two roots for these quadratic equations. These two roots are exact solution, or in other way, they call it analytical solutions. But there are some limitations with the analytical solution. So first one is, when we want to solve complex equations, sometimes it's too difficult to find the exact solution, or it's very time consuming, or even in some like severe situation, it's impossible. So this is where we need to use another method to solve an equation. So this is an example that it's very hard to find the analytical solution. This is an example of partial differential equation. So now the question is, what is numerical solution? Numerical solution is defined as a very close answer to the exact solution, which means that it's not exact. What does it mean? That we have an error. So, but that error is small enough not to introduce like a mistake in our calculation or affect the results. In other words, the error is negligible. And when we want to do the numerical analysis and find the solution, we need to make sure that this condition is satisfied. So when we want to design something or when we want to solve an equation, we need to know that what maximum error we are allowed to have here. So in the mathematical way, fx1 minus fx should be less than the maximum error that could be in our problem. But the good point about the numerical solution is it has less computational cost as compared to the analytical solution. And the other point is we can use the numerical analysis for the complex problems. Could be complex equations or could be complex domain, which the finding an analytical solution is very hard there. So here is one of the severe situations that it makes it very difficult to use the analytical analysis. So you remember from the strength of material or theory of elasticity that we have some standard formula to find the stress or strain or deflection. For example, when we apply pure bending onto the beam, we know that the normal stress, sigma, would equal to my over I. You remember that formula? So this is a standard formula. But that one is only true for the specific geometry and specific loading. So when we have a complex structure, we cannot use that standard formula anymore. Or we need to be cautious to just make some simplification and some assumptions that don't affect the accuracy of the analysis. So here is an example. So when we have like a cantilever beam here, and we apply an axial load to the beam, you remember that as long as it's a linear elastic, the stress is less than yield strength, the elongation in the beam would be delta L equals to FL over EA. F is the force, L is the initial length, E is the Young modulus, and A is the cross section. And what we assume here is we have a uniform material here. We have the cross-section doesn't change here. If any of these conditions are not true in the analysis that we want to do, then we need to be careful when we want to use this formula. And the next case is there are so many applications that involve complex shapes or complex boundary conditions and loading and even multiple materials, which make it very difficult to use the standard formula for the whole thing. So this is a finite element analysis of an aircraft's wing. So this is basically showing the maximum deflection and apparently deflection contour all over the wing. But if you look at we can just consider it as a cantilever beam, but the thing is, the geometry is more complex than a simple beam. So if you look at the cross-section, it's so different. Like, it varies within the length of the wing, and we have like a different morphology or at each section of the wing, which makes it difficult again if you want to use the standard formula for this, just finding the analytical solution by using the standard formula in theory of elasticity. So finite element analysis is one of the numerical methods, which is basically a computational scheme to analyze or solve a problem in so many fields of engineering, science, physics, or mathematics. It doesn't limit only to solid mechanics. This is like a method of solving a problem. And this technique is widely used in different areas, like stress analysis, fluid mechanics, heat transfer, or even electrical or magnetic fields. So the fundamental concept of the finite element analysis is we basically simplify the equation or the problem that we want to solve. How? By breaking down the geometry or the domain to the small area. So instead of satisfying the equation, could be like partial differential equation, all over the domain, we only try to satisfy it in the small domain, which makes it easier. So this is an example that it's divided by the small pieces. So each piece here is called an element. So each triangular here is called an element. And the corner or the verticals the points are called nodes. So these are the two parameters that are very important to define the size of, to define how we do the finite element analysis. So just remember these two terms, element and node. So, sorry. So when we want to solve an equation, we usually have independent variables and dependent variables. And most of the time, dependent variables are unknown, right? Like y equals to x squared. X is independent variable and y is a dependent one. So basically we know that how x varies like within the range, could be from 0 to 5, and then we want to know that how y varies within that range of the X. So in finite element analysis, the relation between the dependent and independent variables could be different based on how we want to simplify the problem. So we can simply, what's the simplest relationship between the dependent and independent variable? Using a linear function. This is the the simplest form of the relationship, right? For the small area. But if you want to be more accurate, we can just use the polynomials relationships. So these relationships are called shape functions. Don't worry about it. I'm going to explain it in details in next lectures. But just remember these terms: node, element, shape functions. I'm going to tell you more about it in the next lectures. So when we divided the body of the an object or the structure to the small pieces, which are called elements, we also have nodes at the verticals of the that pieces, right? So we usually report the values of the dependent variable at the nodes, and we call it nodal values. And if we know the nodal values based on the shape functions, which I explained in the first paragraph about being a linear relationship or polynomial relationships, then we can find the values for all over the points within the element, not just at the nodes. So this is an example of the dividing a thin plate with a hole to the small elements. So as you can notice here is, at some section of the plate, we use the small elements or fine elements, and at some points, we just use the bigger element. So when we use the bigger element, we basically increase the speed of solving the equations, or in other words, reducing the computational cost, right? But when we go for a very fine elements, like a small elements, we increase the accuracy. However, we increase the computational cost. So this is a trade-off here. It totally depends on our engineering judgment to if we want to go for small elements or big elements. Should we sacrifice the accuracy, or should we increase the speed of the solving? So it all depends on the situation and the physics of the problem that we want to analyze. For example, if we can see that at some point, especially like in this plate, we have high stress concentrations, which means that the variation of the stress at those areas are high, right? So we need to capture those variation carefully. So how we can do that? By making the elements smaller at those areas, by increasing the accuracy. But if you feel that, if you can just see, based on the calculation, see that at some sections, we don't really need a high accuracy, we can just go for coarse element, which is a bigger element. Again, I'm going to tell you more about the tips, about choosing the element, choosing the size, choosing the shape functions in next lectures. So if I want to summarize the advantage of FEA, by using the FEA, we can model complex geometries. We can handle every boundary condition and every loading. And it doesn't matter that if the structure has multiple material or it's only made of one single material. And FEA is a very powerful tool that it allows us to just play around with the accuracy and with the speed of the solving the equation. So we can just adjust that. Depends on the situation and the physics of the problem that we want to solve. And it's not only for static analysis. We can also use it for the dynamic and time-dependent problems. Any questions so far? Right. Right. So the basic concept of FEA. So this is an example. So if you look at the left-hand side figure, you can see the analytical solution for the one-dimensional temperature distribution. Imagine that we have a heat exchanger, and we want to know that how temperature varies like in one dimension, like in x, within the x-axis. So this is the analytical solution that we got. And now, if you want to use the numerical method like the FEA and just compare it to the analytical solution, so it's pretty much like that we divided the heat exchanger to the small pieces and then try to find out that how temperature changes in those small elements, right? So if you look at the right-hand side figure, you can see that we have like 7 small pieces. Each piece is called element. So we have 7 elements here. And we use the simplest relationship between the temperature and x, right? Which is the linear. So we just use the linear segments for each element. And as you can see that although we use the simplest form, which is the linear relationship, but we are able to produce the acceptable solution as compared to the analytical one. And if you worry about the accuracy, you can just increase the number of the pieces to increase the accuracy, or replace the line segments with like the second order polynomial function. Just make it more accurate. So this is for 1D, and if we want to do the discretization in 2-dimensional space, this would be an example. So here, instead of the line segments, we have the like a very thin plates, very small plates. So again, each like a rectangular pieces called an element here. And each element has how many number of nodes? 4 nodes, exactly. So this is what I said about the increasing the accuracy in 2 ways. So again, this is the like a exact temperature distribution in the top figure. So we have 2 ways to just discretize the temperature distribution by using the small pieces or elements. So if you look at the left-hand side figure, we have 4 line segments, or we have 4 linear elements, right? We have 4 elements, and in each element we use a small piece of line. And each element has 2 nodes. Now, if you want to swap the the line segments with a higher polynomial function, we can just simply use the second order polynomial function. So this time, instead of using the higher number of the elements, we can use only 2 elements, but since it's polynomial function, it's a second order polynomial function, we need 3 points to define that second order polynomial, right? For defining a line, we only need 2 points aligned with that line to find it out, right? But for the second order polynomial, we need 3 points. So that's why that we use 2 elements, but each element has 3 nodes. So instead of having only 2 points at the end of the line segment, we added another node at the mid edge of the element. So these are the 2 way to increase the accuracy. Increasing the number of the element, making the elements smaller to capture all variation and changes in that area, or using a higher polynomial function as a shape functions. So there are different common types of elements, and it's very important to know all the elements. There are so many people in industries, they know how to use a finite element commercial software like Abacus, ANSYS, or COMSOL, but they don't have a deep understanding of to choose what type of element for each analysis. And this is where it will distinguish a knowledgeable engineers from the normal people that using just learn how to use the software. So I will explain this topic in details tomorrow, but just briefly pointing out the types of the element. We have 1D element, like the temperature distribution that we used. So it could be, probably you heard about these elements, trusses, beams, or it could be 2D, two-dimensional element. Based on the shape, it could be like a 4-node, like a rectangular, or it could be 3-node, like a triangle. And the most complex element is the 3-dimensional one. Could be like a cube, or like a brick, or tetrahedral element. So when we go for the most complex element, which is the 3D element, we basically increase the accuracy, right? Just compare this complex element with the 1D one. I mean, in the simple brick, we have 8 nodes for each element, but for the 1D, we have only 2 nodes. And the important point about the 1D element is, in reality, we don't have any 1D object, right? We don't have any 1D object. But in terms of the mechanics, some of the problems can be simplified into the 1D or 2D problems instead of solving 3D. So basically, we reduce the computational cost and make it much, much easier to do the analysis and solve the equations in that problem. So I will explain all these element types tomorrow. And then the final thing I want to tell you today is, so all right, we just realized that if we increase the number of the elements, if we're using the higher shape functions, we can increase the accuracy or reverse, right? But now the question is, what is the best model if we want to analyze a structure or an object or a problem? What is the best? What is the definition of the best model? So does it mean necessarily that the most detailed model always gives the best result? So the more intricate model is the best one or not? So this is a good example. It's basically my PhD project. I just put it in one slide for you. This is the red blood cell. So if you know about the biology, red blood cell is the simplest cell in our body. It only has two components, a membrane, a thin membrane, and cytocell or fluid inside the cell. It has no nucleus or mitochondria or any other components inside the cell. It has only two components. So the model that I use in my project is I use this important hint. Cytocell, I mean, you know about the fluid. All the fluid are incompressible, right? All the liquid are incompressible, which means that they keep, I mean, here, the cytocell keeps the cell volume constant under the deformation. So it doesn't matter like how we press the cell or how we extend the cell, the volume inside the membrane is constant all the time. It's very interesting to tell you that this cell is able to squeeze into the small capillaries with diameters less than half of the cell diameter. It's crazy. So the cell has a diameter of 8 micron, but they can squeeze into the capillary even with 3 micron diameter. But still, they keep their volume constant and unchanged. So how I use this important point in my model? So when I developed the FEA model, I only model the membrane of the cell as a thin shell. And then instead of the cytocell, I just used a simple mathematical constraint. I just used the constant, volume constant constraint to just regard the cytocell in my model. So I didn't use any fluid elements, and I didn't use any like the solid fluid interaction, which makes it much, much faster and easier. But sometimes this type of simplification are not possible. It totally depends on the analysis and what you want to get from your model. And the last example for today is, you all know about the dam, right? So we have a large volume of water at back of the dam. And now imagine that we want to analyze the structure of the dam to see that what's the stress distribution all over the dam. So if you want to just use the FEA in 3D dimension, in 3D space, this is how we can just create the geometry of the dam, right? And then apply the hydraulic pressure at back of the dam. And also make sure that the two end sides are constrained, like by soil or by any fixture that they use for building the dam. But there is an important point here. Instead of modeling the dam as a 3D object, we can simply use a 2D object. Why we can do that? The answer is, if you look at the physics of this problem, you can see that the geometry is consistent through the thickness, right? The cross-section is consistent. And if you look at the loading, which is the hydraulic pressure, it's consistent through the, not thickness, through the length of the dam. So which means that instead of modeling the whole thing in 3D space, we can simply just model one cross section of the dam and apply the hydraulic pressure at back of that 2D dam, and then do the analysis. And it would be very high accurate as compared to the 3D. So we're going to have something similar to this, just modeling the 3D and 2D or 3D, 1D, and compare it like by using Abaqus to see that how accurate the 2D or the 1D one is as compared to the 3D model. Any questions? Yes?
In the actually scenario, the dam is like bending like a curve, but not like pretty straight. Does it matter if we use the 2D element?
Exactly, it's very important. So the assumption that I used here is, I assume that the cross section is consistent. It means that it's not bended. It's very important. These are the little things, but if you don't consider it, you're gonna have wrong results.
So which cross-section exactly is that?
It could be any cross section because it's consistent through the.
In this case, it doesn't matter.
No.
Okay.
I'm gonna tell you why in the, I think tomorrow.
Okay. Great.
Yes.
Is there any distinct difference to use FEA dedicated software like Epicus and Console compared to those 3D modeling software that they have inbuilt FEA like SolidWorks?
You mean just importing the geometries into the software, like a finite element analysis?
Yeah, because I found that like most people, they are not recommended to use the inbuilt FEA analysis that inbuilt inside the modeling software like SolidWorks.
I see.
Yeah.
So the thing is, most of the finite element commercial software like Abaqus, COMSOL, or ANSYS, they have simple tools to create the geometry there.
All right.
So that's why people usually use the SolidWorks or CATIA to create the geometry, or even sometimes they create the geometry from the microscopic images or CT scan images and build the 3D geometry and then import it into the software.
I see. All right.
Any other question? Yes? Sorry?
When we come to the workshops, are we supposed to install the software? Is it allowed for us, or should we?
Fortunately, we have the teaching license on all the engineering lab, so don't worry about it. But the other good thing is you can download the student version of Abaqus on your laptop to just learn it yourself at home. But there are some limitations based on how many number of the elements that you can use in the student version. So in the student version, the maximum, I'm going to tell you about more, but in the student version, you can only use 1,000 elements. But the other things like how to define the material, how to define the elements, all the same, but you can just run the simulation. Any questions, guys? All right, I'm going to finish off here. Thank you so much, and I'll see you tomorrow.
I'll Google it. Thank you.
Quick question. So I've actually registered for the Friday workshop.
Yeah.
But on the document that was provided for the course outline, it's not.
Are you the one that sent me an email about it? All right.
Because
The others, send me. The thing is, the timetable is not updated. I updated. I think I updated. I don't know if it does come into effect or not, but I uploaded again. So no, it's alright. We're gonna have Friday for sure.
yeah, and that's on like a 207 to 221.
Yeah, 3 to 5. Yes. I see. So the thing is, red buses are very deformable.
Yeah.
But in some like area or sickle they lose their deformability. Because of a couple of factors like the geometry, like the morphology of the cell, also changing the structure of the membrane because the parasites, I don't know if you how much you know about.
I know a little bit.
Yeah, so when the parasites invade the cell, they just export the proteins into the membrane and just build in like their own structure.
So you're modeling on the nerves.
Basically, like 2 years experiments and then 1 year.
I was just wondering,
Yeah. No. Hey. I'm trying to work on something like a fat roll.
Yeah.
I'm working on it. This is my sister. You're a master's here? Master's? Yeah. This is my specimen. I will just initiate the track here. But this has 2 different materials.
Yeah.
I just want to check the track growth pattern.
Yeah.
But there is a problem like track propagation. Yep. This happens
Yeah.
when there's losing indicators. Yeah. Let me just grab my stuff.
Yeah, so just do you prefer Mac or PC?
I don't do Mac.
Sorry. Stop this person. Oh, so what often happens is that you will finish a lecture before the recording finishes, which is normally fine because it turns off automatically. But sometimes students will come up and talk to you at the end of the lecture, and so you want us to stop it. So just to stop it,
So that just means
and we're going to be on someone else's recording right now. Hit that, and then you just press stop recording, and then you have to